In Chapter 8, we're going to begin looking at a group of functions and equations known as quadratic equations. Now, it's turned out that so far in this semester, in this term, you have seen quadratic equations in the applications that we've done. In every case that a quadratic equation has showed up, it has been one that we can use our factoring technique for solving. Now, when I say quadratic equation, we will define this formally, but what I'm talking about is ax squared plus bx plus c is equal to 0. Right? When you have a square of your variable in the equation. It's a polynomial equation, so we have a technique for solving it. Well, it turns out that you're not always able to solve quadratic equations by factoring. Some quadratic equations don't factor. And if that is the only technique we have for solving these things, then there's going to be a whole lot of problems out there we're not able to solve. But it turns out we are able, in fact, to solve quadratic equations that don't factor. And that's what we're going to begin this chapter by covering. In sections 8.1 and 8.2, we cover a couple of different techniques that we can use for solving all quadratic equations. After that, we will take a closer look at some of the applications that we've seen come up over the course of this term. But now we can actually solve all variations of those types of problems. We will also take a look at quadratic inequalities later on in this chapter. All right, so let's get started. We start off by taking a look at something known as the square root property, which says the following. If we have a is some positive number, that is the right-hand side of an equation of this form, x squared is equal to a is positive, then what we can do to solve that is take the square root of both sides. In effect, we have that x is equal to plus or minus the square root of a. So in addition to square root of both sides, you also put a plus or minus out in front, right? I mean, that makes sense if you think of it in terms of a particular example, like x squared is equal to 4, right? There are two solutions to that. X is equal to 2, because 2 squared does equal 4, right? And there's also x is equal to negative 2, because if I square negative 2, I also get 4. All right, so the way that we will think of this is we're going to take this equation, and to solve it, we're going to take the square root of both sides with a plus or minus. Now, let me do an example of a problem. Looks like this. X squared minus 9 is equal to 0. I can use the square root property to solve that by first getting the x squared by itself, adding 9 to both sides, and I have x squared is equal to 9. Now, if I take the square root of both sides, remembering to put a plus or minus in there, x squared of x squared will cancel out, leaving me x, and I end up with x is equal to plus or minus the square root of 9, which is 3. So I have x is equal to plus or minus 3, or another way of thinking of that is x is equal to 3 or negative 3. Right, it's two different solutions. Okay? All right, let's look at the next one. In example B, again, we want to get the x squared term by itself, so I'm going to begin by adding 11 to both sides to move the 11 to the right-hand side, which gives me that x squared is equal to 30. Taking the square root of both sides, using the square root property, I end up with x is equal to plus or minus the square root of 30. Now, I cannot simplify the radical, the square root of 30, any further, so that is the final form of my answer. Please take note that that is still two real number values. Those are two real number values, the square root of 30 and the negative square root of 30. All right, what about example C? Same goal. Let's get the x squared by itself so that I can use the square root property. Begin by subtracting 9 from both sides. That leaves me with 4x squared is equal to negative 9. Dividing both sides by 4 to get the x squared completely by itself will give me x squared is equal to negative 9 over 4. which I will now take the square root of both sides, remembering to put plus or minus on the right hand side. Now what that leaves me with is an x is equal to, now let's take the square root of negative 9/4. We can do the square root of the top over the square root of the bottom. The square root of negative 9, remember from section 7.7 that when you take the square root of a negative number, it's the square root of the value, the absolute value, which is the square root of 9, which is 3, and then the square root of negative 1, which is simply I, over, and the square root of 4 is going to be 2, and I still have the plus or minus out front. So plus or minus 3i over 2. So it's possible, using the square root property, that we will end up with complex or imaginary answers. In this example, notice how we do not have an x squared by itself, but in fact we have now a binomial that is squared. One approach might be to multiply this out, to take the square of x minus 3. To do that, you would have to FOIL. But let me propose that there is another way to handle this. Since we have something squared on the left-hand side, why not use the square root property right away? Why not take the square root of x minus 3 squared equals the square root of 10 with a plus or minus out front? What happens when we do this? Well, according to the square root property, the square roots and the square will cancel out. I'm left with x minus 3 is equal to plus or minus the square root of 10. Notice now that we do not even have a square in our problem, so it's just like a linear equation. All we have to do is get the x by itself, which we can do easily by adding 3 to both sides. So what do I end up with? Well, I end up with x is equal to a positive 3 plus or minus the square root of 10. Now those are two real number values, right? That's 3 plus the square root of 10, which I could plug into my calculator and get a real number. I can also do 3 minus the square root of 10. Those are my two solutions, 3 plus the square root of 10 and 3 minus the square root of 10. I will certainly accept either one of these forms for the answer. But we've been able to solve something that was originally a square problem, a quadratic problem, but had more than just x squared in there. Now this is going to turn out to be a very important principle that we use, because we're going to take general quadratic equations that aren't in this factored form and figure out a way to convert them into this. That's what completing the square is going to be all about. If I can have one side written as a perfect square, right, as something squared equals just a number on the right hand side, I can use this technique to get a solution. I can use the square root of both sides to solve it all the way down and get my solution. Okay. So, in order to do that, in order to do the complete the square technique, we need to talk about something called perfect square trinomials. Perfect square trinomials. These are patterns that we need to be able to recognize. Now notice in these two examples that x squared plus 4x plus 4 will factor. Right? If I try to factor these in the following way, I get this. I get an x here, a plus 2, and a plus 2, which is the same thing as x plus 2 squared. On the other hand, if I try to factor this one, which has the same first terms and the same last terms, x plus 1 and x plus 4 is what I get, which is not a perfect square. Right? So there's something to notice about how the middle term relates to the other two terms. If it's in a certain form, we get a perfect square. If it's in another form, we might not. Now here's how we figure that out. If you have your binomial of this form, x squared plus bx, if we add to that half of the middle term, that is half of the b, and square it, a perfect square will result. That's exactly true in this example right here. If I took the 4 and divided it by 2, and then square that. 4 divided by 2 is 2. 2 squared is 4. I get the last term. hence it's a perfect square. That's not true here. Half of 5 is 2.5. 2.5 squared is not 4. That's why this is not a perfect square. Now look at these two examples that I have down here. I have the first two terms. The question is, what do I stick in the blank so that it's a perfect square? Well, you take, in the first example, you take that -2 that's right here, and you cut it in half, divide it by 2. That gives you what? -1, right? And then you take the -1 and you square it, and you get +1. That's what you're going to add right there. And if you factor that, what do you get? You get x minus 1, quantity squared. All right, what about if you have x squared plus 6x? Okay, if you take that 6 and divide it by 2, you get 3. Take that 3 and square it, you get 9. Right? So right here is x squared plus 6x. If I stick a 9 there, half of the 6 quantity squared, I get something that factors into perfect square. And in fact, the thing that it factors into is an x plus 3. I want you to see this. This 1 right here is the same as this 1 right here. This 9 is what we got by this 9 right here. That is taking half the middle term and square it. Also notice that once it's factored, that 1 right there came from, in fact, it's a -1. You see that? Came from this -1 right there. This 3, which is positive, came from this 3 here. Using the principle that we just came up with, we are now going to develop a technique, or I'm going to state the technique for solving a quadratic equation. A quadratic equation is an equation of this form using something called completing the square. All right, we're basically going to try to, well, what we're going to do is we're going to move the c to the other side. We're going to have these two terms left, and we're going to use the technique for making it into a perfect square that we saw before. And in fact, once we do that, pardon me while I scrolled it back up, once we factor the left-hand side, we're going to have something look like our example D up here, and then we can get all the way to the solution. So we're going to be able to start with an equation that looks like this, complete the square, turn it into an equation that looks like this, and then get the solution. From start to finish, that's how it's going to look. So here are the steps. First step, to solve a quadratic equation by completing the square, and you only have to do this if there is something besides a 1 in front of the x squared term. Divide both sides by the coefficient of the x squared term. Then move the constant to the other side. Step 3 is the main step here. It's the complete the square step. You calculate 1/2 of the coefficient of the x squared, of the x term, and square it. Then add this constant to both sides. Now, by adding it to both sides, I don't change the solution to the equation, but I create on the left-hand side something that will be a perfect square. Then you factor the perfect square trinomial on the left. Then you use the square root property, as we did in the previous examples, to solve. And finally, once you get a final answer, something you can always do with solving equations, is to check your answer. Plug it back in if you want to. Now, number 6 I won't do every time. In fact, I probably won't do it at all here in the notes, but you can always do that if you want to confirm that you've got the right solution. You check it by plugging it back into the original equation, making sure that it is in fact a solution. One very helpful thing to point out is that this technique does not create extraneous solutions. In the last two chapters, both chapter 6 and chapter 7, the material we covered whenever we solved rational equations and when we solved radical equations, we had to confirm whether or not our solutions were in fact extraneous. We had to check, plugging back in the solution to see if in fact it was a solution. In this case, you can check, but you're not required to do so, assuming you made all the correct steps, right? If you did everything correctly, it is a solution. While in the previous chapters, you could have done everything exactly correct, but still create an extraneous solution. That's not going to happen here. All right, so let's do a couple of examples now. To begin with, we have x squared plus 4x minus 1. You'll notice right away if you give this a shot, you can't factor this, so factoring is not an option. If you look at the steps from before, we do not have an a term, so we don't have to do step 1. We don't have anything besides a 1. We just got a 1 just in front of the x squared. So I begin by adding the constant to both sides. Move the constant to the right-hand side. I have x squared plus 4x. I will leave a blank here to fill in, and I have a 1 on the right-hand side. Now the question is, what goes right there? I remember I take 4, divide it by 2, and I get 2. I always divide it by 2. Then I take the 2 and I square it. That gives me 4. So that's what I'm going to add to both sides. 4 and a 4. Okay? Now the result is something that factors on the left-hand side. It's going to become x plus 2. Again, if you factor this, you're going to get x plus 2 times x plus 2, which I can write as x plus 2 squared. The shortcut tells me that that's always going to be the number that goes in right here. That is, the half the middle term is always what ends up inside when you factor. The right-hand side, right, is 5. So this is scratch work in the middle here. Now, if I have x plus 2, quantity squared is equal to 5, I take the square root of both sides, putting a plus or minus on the right. The square and the square root cancel. I have x plus 2 is equal to plus or minus the square root of 5, which if I now subtract 2 from both sides, my final answer is that x is equal to negative 2 plus or minus the square root of 5. I can't simplify the radical any further, so I leave my final answer in this form.
On example B, we're given 2x squared plus 3x minus 4. Of course, we want to solve for x when this is equal to 0. In order to do this, the first step we need to do is divide through by the a, right? We need a 1 in front of the x squared in order to complete the square. So we're going to divide everything here by 2 all the way across. Okay. In effect, I'm dividing the whole left-hand side by 2, which means I can divide each individual term by 2, which gives me x squared plus 3 halves x minus 2 equals 0. Now what I'm going to do is I'm going to move this 2 to the other side. I'm going to have x squared plus 3 halves x space and then equals 2. Now we need to take half of the middle term. So that means I got to take 3 halves and I want half of that. So the way I take half of that is to multiply by half, which gives me 3/4, which means now I'm going to take 3/4 and square it, which gives me 9/16. That's what I want to add to both sides. This, and I'm going to add 9/16 over here. Okay. Now the left-hand side will now factor. Remember, the shortcut for factoring is that the second term in your binomial is actually this term right here. In our case, the 3/4. That's what you get when you took the half of the middle term. So this is plus 3/4 squared. That's what the left-hand side factors into. And now for the right-hand side, I need to combine 2 plus 9/16. So finding a common denominator means I'm going to multiply by 16 over 16. Or 32 plus 9 gives me 41 over 16. Now we square root both sides, remembering the plus or minus. We end up with x plus 3/4 is equal to the plus or minus the square root of 41 over 16, or the square root of 41 over the square root of 16, which is 4. Now if I subtract the 3/4 to the other side, what I'll end up with is x is equal to negative 3/4 plus or minus the square root of 41, all divided by 4. Now I can't simplify inside that radical any further, so this is the final form of my answer. Okay, so again, step by step, we went through, divided off the a, moved the c to the other side, we completed the square, we factored the left-hand side using our shortcut. We simplified the right-hand side, then we took the square root of both sides, and then we isolated the x term. And that's how we ended up with our final answer. Our last problem here is a word problem where we're asked to consider the following scenario. A 50-foot supporting wire is to be attached to an antenna. So imagine that you've got an antenna drawn, we'll go straight up and down here, and attached to it up here at the top we're going to have a supporting wire come down off the top. Okay, and that wire is to be 50 feet long. Okay. We also know that the wire is anchored 20 feet from the base of the antenna, so this horizontal distance right here is 20 feet. Okay, we're assuming, of course, the ground is level, so that forms a right angle. The question is, how high up the antenna should the wire be attached, maintaining that this is 50 feet and this is 20 feet. Okay, now the antenna may extend upward from that point. The question is, what's the size of x? Now, as hopefully you know, we're going to use the Pythagorean theorem here because the ratio of the right, or the relationship between the sides of a right triangle are given by a squared plus b squared equals c squared, where a and b are the sides and c is the hypotenuse or long side of the right triangle. We're also asked to simplify our answer in radical form and also find a decimal approximation to the nearest tenth of a foot. Alright, so let's plug in what we know. The sides are x and 20, so we have x squared plus 20 squared is equal to 50 squared. So if we multiply that out, we have x squared is equal to plus 400 is equal to 2500. And to solve for x, we're going to subtract the 400 from both sides. We end up with x squared is equal to 2,100. And so take the square root of both sides. We end up with x is equal to plus or minus the square root of 2,100. Now the first thing we know is this is obviously positive because we're dealing with distances or lengths in the real world, which is always a positive value. Now if we want to simplify that in radical form, we need to split this up into a number times a perfect square. In this case, I can clearly see 100 goes into 2100 21 times, and 21 does not have any perfect squares. So this ends up being 10 square roots of 21 because the square root of 100 is 10. The square root of 21 is the 21 is a leftover. It stays inside of the radical. Okay, so that's the first part of our answer. It also asks us to find a decimal approximation, so I'll go to my calculator and I'll type in 10 times the square root of 21, which gives me 45.8 feet. And that concludes section 8.1.